Assalamualaikum and good day. I hope everyone is in good condition and please stay safe. Today, I would like to discuss about sequence impedance in symmetrical component topic. You can refer all the notes in Chapter 5 PowerPoint slide through our Google Classroom. Make sure you have it ready and jot down any important notes. As we have discussed in the previous subtopic, the term sequence means that we will have three impedances depending on the sequence, which is Z1 for positive sequence impedance, Z2 for negative sequence impedance, and Z0 for zero sequence impedance. And the term impedance is the impedance for the network component such as loads, transmission lines, generators, and transformers. In power system, we will use one line diagram to represent the network. By referring to the one line diagram, the first part is a generator. The second part is the transmission line, including the transformers. And the third part is the load. The generator synchronous machine has four different impedance connections, which are Y connection, Y to ground connection, Y to ground with ZN connection, and delta connection. For the transformer impedance connection, there are 6 combinations of impedance connection. First, YY connection. Second, Y to ground with Y connection. Y to ground with Y to ground. Y with delta. Y to ground with delta, and the last one is delta-delta connection. For the load, in this analysis, we will only consider the load with Y connection. To analyze the system's unbalanced fault, we must identify 3 different sequences of the one-line diagram circuit first, which is positive sequence, negative sequence, and zero sequence. Before we determine all the circuit of the one-line diagram sequences, let's take a look at the impedance connection of generator synchronous machine. The figure shows the positive sequence network of synchronous machine, where figure A is the 3-phase model and figure B is the single-phase model. In one-line diagram, we can represent this synchronous generator as this symbol. So this is the symbol for the generator in one-line diagram. Before we determine the positive sequence network or positive sequence diagram, we must convert the 3-phase connection into the single-phase connection. Since the 3-phase connection is balanced, so we use phase A to represent the single-phase diagram. Therefore, based on figure B, we can see that in single diagram, it only has one internal voltage, which is EA, and one positive sequence impedance Z1. To draw the single-phase circuit diagram, the internal voltage EA must connected to the reference bus, and the positive sequence impedance Z1 must connected to the EA internal voltage. To draw the single phase diagram, the internal voltage EA must connected to the reference bus, and the positive sequence impedance Z1 must connected to the internal voltage EA. The current that flow in the circuit single phase diagram we call as a IA1, and meanwhile the voltage potential between reference bus and node A is VA1. Apart from single phase model as shown in figure B, we can draw the single phase diagram in other ways. For example, in positive sequence network of synchronous generator, as I mentioned before, the diagram must have an internal voltage EA and positive sequence impedance Z1. The internal voltage EA is connected to the reference bus, and it also connected to the positive sequence network Z1, where Z1 is connected with the node A. The current that flows in the circuit is named as IA1, and the voltage potential between reference points to the node A is VA1. So this is the other method that we can draw the synchronous generator positive sequence network. Now we proceed to the negative sequence network of the synchronous machine. To draw the diagram of negative sequence, we need to convert the three-phase model into the single-phase model as same method as positive sequence network. In contrast to the positive sequence, there is no internal voltage in the network. Negative sequence only has negative sequence impedance Z2 that connected to the reference bus, as we can see in figure B. Besides figure B, we also can draw the single line diagram in other ways, like we draw the single line diagram for the positive sequence network. So for example, in negative sequence, we have negative sequence impedance Z2 that connected to the reference bus or to the ground, and the other side of Z2 we connected to the node A. So the current that flow in this circuit we name as the IA2, and the voltage potential between the reference points and the node A is VA2. So this is the two different methods that we can draw single phase diagram for the negative sequence networks of synchronous generator. Next, I would like to discuss the zero sequence network of synchronous machine. Zero sequence network of synchronous generator can be divided by four different connections, which is first Y grounded with Zn, second solidly Y grounded, third ungrounded Y, and fourth is delta connection. Now we discuss how to convert three-phase model zero sequence network of synchronous machine with Y grounded Zn to the single phase model. First, we look at the three-phase connection. As shown in figure A, we can see that the Y connection of generator is connected to the ground with impedance Zn at point N. To draw the single phase diagram, we only consider phase A. So we can draw the circuit between ground and point A, where the ground we mark as a reference bus. Therefore, the current will flow from the ground to node A. Thus, in single-phase model of zero-sequence network, it only has impedance Zn and zero-sequence impedance Z0 that connected to the reference bus. If we notice in figure B, Zn in single-phase model, we need to multiply by 3. Why we need to multiply Zn by 3? At point N in figure A, we can write the current equation using KCL method. So the current IN is equal IA0 plus IB0 plus IC0. Since the generator connection is balanced, the symmetrical component IAO equal to IBO equal to ICO. Therefore, we can write the IN equation equal to 3IA0. Then we can write the voltage potential equation between ground and phase A. The voltage potential equation VAO equal to IN times Zn plus IA0 times Z0. Then we substitute the value of IN, we get 3IAO times Zn times IAO Z0. And then we simplify the equation, we factorize the IAO0, then we get IA0 times 3 Zn plus ZO. So this is how we get 3 Zn in the single phase diagram. Then we can redraw the circuit in figure B. So we have 3 Zn that connected to reference bus or ground, and the N connected to negative sequence impedance Z0 and node A. So the current is IAO and the voltage potential is VAO. Now we proceed to the second connection of the zero sequence network of a synchronous generator with solidly Y grounded. For this type of connection, we can see clearly in figure A that the node N or neutral point is connected directly to the ground without Zn. Thus, to draw the single-phase model, node N will be connected to the reference bus and also connected to the negative sequence impedance ZO, as shown in figure B. Then we can redraw the single-phase diagram. In single-phase equivalent circuit, we have zero sequence impedance of generator Z O G for generator that connected to the reference bus, and it also connected to the node A or phase A. And then the current that flows into the circuit is IA0, and the voltage potential between reference points and node A is VA0. The third connection of zero-sequence network of the synchronous generator is ungrounded Y. For this connection, node N is not connected with ground or impedance Zn, as we can see in figure A. Thus, in single-phase circuit, the node N will be disconnected to the reference bus as well, but it's connected to the negative sequence impedance Z0. So we can redraw the single line diagram like this. We have zero sequence impedance of generator ZOG with node N, where node N is disconnected with the reference bus, and the impedance is connected to node A or phase A. And then the current flows in the circuit is IA0, and the voltage potential is VA0. So we can draw the single phase diagram like this. We have zero sequence impedance of generator ZOG with node N and node A, where node N is disconnected with the reference bus. And then the current is IA0, and the voltage potential is VA0. The last synchronous generator zero sequence network connection is delta. For this connection, both ends of negative sequence impedance will be connected to the reference bus, and there is a gap between zero sequence impedance and node A as shown in figure B. To make it easier to understand, we can redraw the single phase diagram. In single phase equivalent circuit, we have zero sequence impedance of generator ZOG. Both ends of the impedance are connected to the reference bus, and node A is disconnected with the impedance. And then the current is IA0, and the voltage potential is VA0. The next part of one line diagram or single line diagram is load. As I mentioned before, only Y-connected load is considered. For example, figure shows a Y load with natural connection. If impedance Zn is inserted between the neutral and ground of the Y-connected impedances, the sum of the line currents is equal to the current In in the return path through the neutral. From the circuits of Y-connected load, we can write the unbalanced line current equation in terms of its symmetrical components. Based on the circuit, we know that In equal to IA plus IB plus IC. Then we expand each of the phase current to their symmetrical component. So IA equal to IA0, IA1, and same goes to the IB and phase C. Then we rearrange the equation based on their sequence. For example, zero sequence, negative sequence, and positive sequence. So we get zero sequence first, IA0 plus positive sequence and negative sequence. For zero sequence, we know that the magnitudes of zero sequence are equal, but the value of phase displacements is 0. So we can write the equation for zero sequence as 3 times IA0, where we know that IB0 is equal to IA0 and IC0 also equal to IA0. So we get 3 times IA0. Then for positive sequence and negative sequence, the magnitudes are equal and the phase displacement is plus minus 120 degrees. So from previous discussion, we know that IB1 is equal to a to the power of 2 times IA1 and IC1 is equal to a times IA1. Then IB2 is equal to a times IA2 and IC2 is equal to a to the power of 2 times IA2. Now we can write the equation for positive sequence and negative sequence. So the equation becomes 3 times IA0 plus IA1 plus a to the power of 2 IA1 plus a times IA1. Then for negative sequence, IA2. Then we simplify the equation for the positive sequence and negative sequence. So the equation becomes 3IA0 plus, we factorize the IA1 for positive sequence, IA1 times 1 plus a to the power of 2 plus a plus, then we factorize IA2 for the negative sequence, IA2, then we get 1 plus a plus a2. Then if we substitute the value of operator a, we will get I plus a to the power of 2 and plus a is equal to 0. And this one is equal to 0 as well. Therefore, the current for IN is equal to 3 times IA0. From the current equation, IN equal to 3 times IA0, we know that Rn only exists in zero sequence network. If we refer to the circuit, VAN is voltage of phase A with respect to neutral, and VA is voltage of phase A with respect to ground, where VA is equal to VAN plus VN. So from the equations IN and VA, and also from the circuit, we can draw the single phase model or single line diagram of sequence circuits of Y connected loads. Figure A, B and C show the single phase diagram with Y load connection for zero sequence, positive sequence and negative sequence. From the figure, we can see that only zero sequence has impedance Zn that connected to the reference bus. For positive sequence and negative sequence equivalent circuit, the load impedance is connected to the reference bus without Zn. Now We proceed with sequence impedances of transformer. For transformer, the single-phase model depends on the winding and ground connection on each side. But please be reminded that the winding connection of transformer is only considered in zero sequence equivalent circuit. In positive sequence and negative sequence network, the winding connection will be neglected. Figure shows a zero sequence equivalent networks of three-phase to winding transformer banks. By referring to the figure, we can say that there are 6 combinations of transformer winding. First is Y to Y connection. Since both windings are not connected to the ground, the impedance Z0 is not connected to the node R and node S. It also not connected to the reference bus. The second connection is Y grounded to Y connection. For this connection, since only winding at R side is grounded, so the impedance Z0 is only connected to the node R. The third connection is Y grounded to Y grounded connection. In this case, all windings are connected to the ground. Therefore, both sides of impedance Z0 are connected. Next is Y to delta connection. For this type of connection, the winding on R side is similar to first combination. Thus, the impedance Z0 is not connected to node R. Next, there is no ground connection for delta winding. So, the impedance Z0 also not connected to node S. But for every delta connection, impedance Z0 will always be connected to the reference bus. The fifth connection is Y grounded to delta. In this type of connection, the winding on R side is similar to second combination. So, the impedance Z0 is connected to node R, while the winding on S side is similar to fourth combination, where it's connected to the reference bus. Lastly is delta to delta connection. Since both windings are delta connected, so both ends of impedance Z0 are connected to the reference bus. As conclusion, we can use one line diagram to simplify the three-phase system. The diagram must be constructed with respect to the sequence network. For positive sequence network, the one-line diagram must include the synchronous machine, such as generators and motors. For negative sequence network, the diagram is the same as positive sequence, but without any voltage sources. And for zero sequence network, the type of connection for the synchronous machines and transformers must be considered when we draw the one-line diagram, and it also has no voltage sources. That's all for now. See you next time. Bye.